So last chapter for the year, complex numbers and complex functions. So for your class test 4, it will only be the complex numbers part. In the final week of the semester, we will do complex functions. That won't be in the test, but that will be in the exam. Okay, so just to split the two things. So complex numbers up to the last bit on complex equations, that's for the test. Complex functions is not in the test, it is in the exam. Okay, so just to clarify on that. Okay, so let's get started. We begin with the fundamental theorem of algebra. This pen. Okay, if you have not heard of the fundamental theorem of algebra, that's fine. We'll go through it. You won't need to know how to prove it. We'll just state it and use it. But the proof we will not be going through. Okay, the fundamental theorem of algebra. Okay, so you do need to know what it is, you need to know how to use it, but you will not need to know how to prove it. Okay, every non-zero polynomial of degree n has n roots. Very simple to state, but very important. So every non-zero polynomial has of degree n, so your straight lines, quadratics, cubics, and so on, has n roots. Okay, so let's have a look at a little example, and then we're going to see we have to modify this slightly. So let's say we have the polynomial p of x, which is given by 1 minus x squared. So this is a degree 2 polynomial. It's quadratic, so we expect that this has 2 roots. Degree 2. So if we want to find the roots, we take the polynomial, we set it equal to 0, and we solve. So in this case, we have 1 minus x squared. We can factor that as 1 plus x, 1 minus x is equal to 0. So from the first bracket, we get x equals minus 1. And from the second bracket, we get x equals 1. Okay, so we get minus 1 and plus 1. In other words, we get 2 roots. Okay, so everything seems fine so far. Let's have a look at another example. So we have p of x is equal to 1 plus x squared. We want to find the roots, so we take this and we set it equal to 0. Now here we're going to run into a big problem. Okay, so 1 plus x squared, we can do a little graph of this on the side, and we see it looks like this. Okay, so it looks like that. There's no intersection with the axis. So no intersection with the x-axis. So we can conclude, well, there's no roots. There's no x-intercept, so there's no roots. Okay, but that's wrong. Because the fundamental theorem of algebra says that every degree 2 polynomial has 2 roots. So in fact, it's not the case that there's no roots. In fact, there are no real roots. Okay, so let's have a look at the problem again. We've got 1 plus x squared is equal to 0. So x squared is minus 1. And let's just force this to be a solution. We take the roots on both sides. We get x is equal to plus minus the root of minus 1. Now, so far from high school and first year and second year, this would be invalid, right? You can't take the root of a negative. However, for complex numbers, we're going to define this root of minus 1 as a separate number. So we define the complex number. So we're not working with real numbers anymore. We're working with complex numbers. So we define the complex number I. Now here I need to mention something about engineers and the imaginary unit. So this I here is called the imaginary unit. Mathematicians, physicists, and so on call it I. For some unknown reason, I've got no idea why, engineers call it J. I will not do that, okay? But when you get to the module later on in engineering and if you do electrical engineering, you'll see that a lot. They use J. I will not do that. I will use I, but please just keep in mind that later on you will see J. Okay, so just make a note. However, for the rest of this module, we pretend it's R. Okay, so here, just make a note. Electrical engineers, you will be using J next year. Who's doing electrical engineering? 1, 2, okay. So you guys, please make a note. You will be using J next year. Okay. Mechanical engineers, that will be up to your lecturer. Okay, whether you use I or J. But for the electrical, it's guaranteed J. Okay, the others, it depends on which lecturer you get. Okay, so we define this complex number I, which we call the imaginary unit. Okay, so I for imaginary makes more sense than J. And how do we define this? We define it as I squared is minus 1. Okay, that is how this I is defined. In other words, when we take this root here of minus 1, that gives us I. So R squared will give us back minus 1. Okay, you go back and forth. So root minus 1 is I, so R squared is minus 1. Okay, so please put a nice box around that. You'll be using this many, many times as we go through. Yeah?
You just said.
So this number over here, root of minus 1, we call that R. So root minus 1 equals I. So R squared is minus 1. It's just another way of writing this. So we don't want to write this root minus 1 all the time, so we call it R. And whenever you have R squared in your equation, we replace that with minus 1. Okay. So I'll put a note here. So this is, instead of using root minus 1 in our equations. Okay, that's why we say define. Okay, so this root minus 1, we're now going to call I, and from now on we'll call it that. So we have x is equal to plus minus I, which means our polynomial that we had before, the x squared plus 1, we can now factor, not in terms of real roots, but in terms of complex roots. So the polynomial 1 plus x squared can be factored using complex roots. Okay, so 1 plus x squared, that will be 1, sorry, we can write it as x plus I, x minus I. And again, remember, R squared is minus 1. So if you multiply that out, we get x squared plus ix minus ix, that cancels. And then when you do the I times I, remember that's minus 1. So again, I'll put a reminder, R squared is minus 1. So please expand that out on the right-hand side. Note that R squared is minus 1 and show that we get to that left-hand side. All right. Any questions about this I that we've introduced? You're all good. Okay, so we're going to make a slight modification to this fundamental theorem of algebra. So here we said has n roots. We're now going to specifically say it has n complex roots. And that includes the real roots. So every real number is a complex number. Not every complex number is a real number. We'll see that shortly. Okay, so every non-zero polynomial of degree n has n complex roots. So when we say, when we specify the roots of a polynomial, we need to be careful which number system we're using. So if you look at 1 plus x squared just over real numbers, then it has no roots. But 1 plus x squared over complex numbers is guaranteed to have 2 roots. Okay, so it depends on what you're looking at. But from now on, we will only be working over complex numbers. Any questions so far? Yep.
So why is x plus I and x minus I instead of x plus I and x plus I?
It's exactly the same as what we had here with x plus 1, x minus 1. They always come in those pairs. So when you factor a difference of squares, it's like a plus b, a minus b, right? You know, difference of squares, a squared minus b squared?
1 minus x squared. 1 plus x squared.
No, they're two different examples. Two different examples. Don't mix them up. Okay. Yeah, this is example 1. And this is 2. Okay, 2 separate things. Okay, so let's define the sets of complex numbers. So the sets of all complex numbers. Pen. So you're familiar with like the sets of real numbers, the sets of rational numbers, and so on. Now we have the sets of complex numbers. Okay, this is given by C with a vertical line. Very similar to how we have the natural numbers as n with the little line there, or the real numbers as r with the little line. Here we have C. Okay, so this is the set of all z. So usually complex numbers are written as z. So other letters are reserved for real numbers, z that's reserved for complex numbers. Such that z is equal to x plus I y. So we know what I is, we know what x is, we know what y is. We form this new number, z, where x and y are real numbers. Okay, so you take real number x, real number y, you form this little sum there with I, and that is a complex number. So, some examples. So z equals I. This is a complex number, so we can see that quite easily. If x is 0, that's a real number, it's fine. And y is 1, then this belongs to the set, so I is a complex number. Z equals 3. This is a complex number. We take x to be 3, we take y to be 0, we get 3. So from this, we conclude that the set of all real numbers is contained in the set of all complex numbers. So every real number is a complex number, but not every complex number is a real number. Okay, so it's a subset. And we can have another example, z equals 1 plus 2i. This is a complex number. We take x to be 1, we take y to be 2, and we get this complex number z. All right. Any questions about these examples? Yep. Nothing that concerns you for now. Okay, so this is just complex number. Don't worry about other things. Okay, so there are other number systems you will see later. Quaternions, if you're doing mechanical engineering, that will be later. I don't want to scare you too much. Okay, yeah, no. If you want to look it up, it's called quaternions. Quaternions. You'll see that later in mechanical engineering. Yeah, but I don't want to scare you with all of that just yet. Right. Any other questions? No. Okay. So let's have a look at some examples of factoring polynomials over complex numbers. Okay, so last year we did a bit of polynomial factoring. Okay, that was over real numbers, but I never said factor the polynomial over the real numbers. We just took that as a given, right? You use your quadratic formula, you got your answer. Now we're going to be very specific, and we're going to say we're going to be factoring the polynomial over complex numbers, which means that we're going to have some complex solutions as well as the real solutions from last year. Okay, so let's have a look. We've got z squared plus 2z plus 3. And from now on, we're going to work with z, not x. X and y, those are going to be real numbers. Whenever you have a z, we assume that it is a complex number. Okay. Yeah, just rather stick to that convention, and then you won't get confused. Okay, so we want to factor this polynomial. It's z squared, so we're going to have two roots. The roots could be real, they could be complex, but we know that the real numbers are subsets of complex numbers, so both of them are guaranteed to be complex in some way. Okay, because remember, z equals 3, that's still complex. Okay, so we're going to set this equal to 0, and we're going to factor it. Now, a quick check with your knowledge of factoring with real numbers. Will this have real solutions? Yeah, your A, B, and C, you can check. Can we write this as x plus A, x minus B, or something like that? Check. No. Okay. So that means all of the methods from last year, trying to factor this, using the this A here, you write it as the prime factors, and the 3 you write as the factors. That's not going to work, right? So we're going to try something else. What we know will always work is the quadratic formula. Always works. Okay, so the quadratic formula always works. Yeah, so even if you can do that factoring methods from before, quadratic formula always works, so we can always use it. So let's do that. So z is going to be equal to, remember the quadratic formula, we're going to be using it a lot. What is it? Minus b plus minus, yeah. Square roots, yep. Minus 4ac, yeah. All over 2a. Good. Please put a big box around this. If you didn't know it before, make sure you know it now. Okay. So we're looking for A, B, and C. So here we have A is 1, B is 2, C is 3. So let's substitute, just treating it as the quadratic formula, and then we'll see how we get our complex solutions out of this. So Z is going to be minus B, so that will be minus 2, plus minus the root of B squared, so that will be 4 from there. Minus 4, A is 1, C is 3. All over 2A, but A is just 1. Okay, so we haven't done anything funny. We've just directly substituted. But this is not going to work on your calculator, right? because that inside part there is negative. You're going to get error or something like that. Okay, so we're going to do it manually instead of using the calculator. I think some calculators can handle complex numbers, but rather not trust it. Okay, now just in case it doesn't work and then you're stuck, you need to know how to do it manually. So we have minus 2 plus minus the root of 4 minus 12. Already we can see some problems with that, over 2. So this is going to be minus 2 plus minus the root of what? Minus 8 over 2. Now this root of minus 8, that gives us some issues. So the minus 1 that's attached to the 8, we're going to take it out. So this is going to be minus 2 plus minus the root of minus 1. That's giving us problems. So let's take it out of the root there. And we're left with root 8 left over. Yeah. Root 8, we can simplify that a bit. That will be 2 root 2. So this will be minus 1 plus minus root minus 1. We know what that is. That will be I. And then we've got root 2. And we see the plus and the minus, we have 2 complex roots. So we have Z1, it's minus 1 plus I root 2, and Z2 is minus 1 minus I root 2. They always come in these pairs. Okay. So Z1, Z2, they come in these pairs, the one with the plus, the one with the minus. Okay, so for homework, use these roots to then factor the polynomial and show that by expanding out the factored polynomial, we get back to the original. Okay, so you're going to write it as Z minus Z1, Z minus Z2. Check that you get back to what we had at the beginning. Okay, number 2, we have Z squared minus Z minus 2. Okay, quick check. Are we going to get complex solutions for this one? Okay, check B squared minus 4AC. Check the sign of it. What do you get? So what do we get?
2 and minus 1.
Okay. Okay, so we have an idea where we're going. Let's say we didn't know that. Let's do it the long way, see we get the same answer. Okay, so Z, that's going to be equal to minus B. So 1 plus minus root B squared minus 4 AC all over 2A. So Z is going to be 1 plus minus roots of 1 plus 8, so that will be 9 over 2. So we get Z is 1 plus minus 3 over 2. Okay, so here we get 2 real solutions. But we know that real numbers are just complex numbers with y being 0. Okay, so these are still complex. So we get Z1. This will be 1 plus 3 over 2. Okay, that will be 4 over 2, which is 2. And Z2, that will be 1 minus 3 over 2. That will be minus 2 over 2. That will be minus 1. Okay. Any questions for this one? Yep. Sure. Okay. Any questions? You're good. Okay, we'll do one more example, then I'll leave 2 for homework. So number 3, we have Z cubed plus 16Z. Okay, yes?
So what's the question going to ask us?
Factor the polynomial. Yeah. So factor the polynomial, find the roots, you know, that kind of thing. Okay, so we have z cubed plus 16z. Okay, so it's z cubed, so we should have 3. There should be 3 answers in the end. So let's set this to 0. We can do some simplifying. So this is z cubed and z. They both have a factor z there, so we can take that out. Okay. Now this z over here, we're not going to get rid of it right away. Let's leave it over there. This inside part, we're going to factor. Okay, so z squared plus 16. If this was z squared minus 16, what would we get? Plus minus 4. That's right. But if it's a z squared plus 16, you can check this, but shorthand, we're going to have z plus 4i, or r times 4, however you want to write it, z minus r times 4. Okay. So it's a little shortcut to see what it's going to be. So if it was z squared minus, we would have plus minus 4, but it's z squared plus, so we have to include the I. Okay, and you can check this. So z times z, that will give us the z squared, plus r times 4z minus r times 4z, that goes away. Then r times 4 times minus r times 4, so we get minus r squared 16, but r squared is minus 1, so we get 16. Okay. Now it's fully factored. We see this is possibly 0, or that one, or that one. That gives us our 3 roots. So z equals 0, that's from the first one. Z equals minus I times 4 for the second. Z equals R times 4 for the third. We see that all of them are complex. Yeah. Again, 0 is real, but we can also take it as a complex number. Okay. And again, the complex parts there, they always come in those pairs, like we had above here. This one over here, the one with the plus, the one with the minus. Same thing happens here. One with the plus, one with the minus. If you're not getting the pairs, you're doing something wrong. All right. Any questions for this one? Yes? No, you just leave it off. Just leave it. Yeah, this root minus 1 we just had right at the beginning, but just use r for everything from now on. Okay, any other questions? Oh, good. Okay, so then the homework problems, number 4 and 5. So we have z to the 4 plus 3z squared. Okay, so here it's z to the 4, so you should have 4 solutions. Check that. And number 5, we have z cubed plus 3z squared plus z. Okay, and this is z cubed, so we should have 3 solutions. Any questions about the homework? Okay, yeah.
For an exam, this goes to
Yeah, it will be up to 4 like that. Yeah, there won't be anything more than that. Yeah, so quadratic, cubic, power 4, if you can do that, you'll be fine. Yeah, any other questions? You're good. Okay, next bit, complex number arithmetic. Yeah, and then just a note for the quiz after the holiday, so the week when we get back, it will be on the factoring that we just covered, and this part, the complex number arithmetic. Okay, that'll be for the quiz. Yeah, just those 2 things. Yeah. yeah, more to come, but that will be afterwards. Okay, so what do we mean by complex number arithmetic? Well, we mean the same thing with real arithmetic, adding, subtracting, multiplication, division, but now with complex numbers. So we'll go through addition and subtraction and multiplying by real numbers now. Then the multiplication and division, you'll read through that in the holiday, and then we'll go through that when we get back. Okay, so addition. So we've got complex number Z1 plus complex number Z2. How does this work? Well, we need to define how we add things. So let's say Z1 is X1 plus I, Y1. For some X1, Y1, we get a complex number Z1. Z2, we write as X2 plus I, Y2. Different complex number, different X and Y. So how do we add them? Z1 plus Z2, this is going to be equal to, so Z1, we can write as X1 plus I, Y1 in brackets for the Z1. And then Z2, we have the same thing, but for X2 and Y2. Okay, so now how do we add them? Well, we're going to take the X1 and the X2. Those are two real numbers. We know how to add real numbers, so we're going to do that. Sorry, X1 plus X2 plus what's left over. We have I, Y1 and I, Y2. We can factor out the I and then add the real numbers. Yeah. So again, X1, Y1, X2, Y2, those are real numbers. We just add them as normal. So if we have X1 and X2, those are real numbers, we just add them. Y1, Y2, those are real numbers, we just add them. Yeah, so we just add the X part and we add the Y part. What about subtraction? You could probably guess what we do with this. So we want Z1 minus Z2. So let's say Z1 is X1 plus I, Y1, and Z2 is X2 plus I, Y2. Okay, so now we want to subtract them. So Z1 minus Z2, how's this going to work? Well, Z1, we know what that is, X1 plus I, Y1, minus, and Z2, we know what that is, X2 plus I, Y2. Okay, you can guess what we're going to do now. X1 and X2, those are real numbers. We can put those together. So it will be X1 minus X2. Okay, and we're left with Y1 and Y2. We can factor out the I. We're left with Y1 minus Y2. Okay, very, very simple. Okay, so this is addition, subtraction. Next, we're going to look at multiplication. Okay, so I'll write out the definition. You don't have to do any examples or anything with that. That will be in the next tutorial. But just what is the multiplication? Let's say we have some real number A multiplied by a complex number Z. Remember, Z is for complex numbers, others, those are real. So we're going to have Z is X plus I, Y. So A times Z, that will be A, X plus I, Y. Okay, you can probably guess what we're going to do next. We just distribute inside. So this will be AX plus I, AY. Yeah. Very easy stuff. Now, multiplication between two complex numbers, that's a bit more difficult. Let's have a look at that. So we're looking at Z1 times Z2. So I'll put a little dot there for the times, but after this, we're just going to ignore that. So Z1, Z2, we take that to be the product. So Z1, X1 plus I, Y1, Z2, X2 plus I, Y2. Okay, this one's a bit more involved, but not too bad. So Z1 times Z2, we have brackets for Z1, X1 plus I, Y1. And brackets for Z2, that will be X2 plus I, Y2. Okay, and we're just going to do it exactly the same as before. We just distribute with the brackets. Okay, same as we did for the addition and the subtraction. Okay, so let's go through it slowly. So we're going to distribute the X1 into the bracket there. So it will be X1, X2. Plus, and then the X1 with the I, Y2. Okay, plus, then the I, Y1, we're going to distribute. So it will be I, Y1, X2. Plus, now we have to be very careful. R times I, that's a minus 1. Okay. So, end of last year, when I was marking the exams, you can imagine how many forgot that R squared was minus 1. It was 0, 0, 0, 0, all the way down. Okay. So please do not forget that R squared is minus 1. Okay, so that's minus 1. So what do? We group together the parts without the I, and we group together the parts with the I. So we have X1, X2, minus Y1, Y2. Those are the parts without the I. We group together. And then those middle terms with the I, we can factor out the I. We get I, X1, Y2, plus Y1, X2. Okay, so that's the method we use to multiply out the brackets. Okay, so it's just your normal distribution. But again, please remember R squared is minus 1. As long as you keep that in mind, everything is as you know it from before. Right. Any questions on this? Yep.
When you're testing us in the first section, you need to know how to do this, what you showed me.
Yes, yes. So if I give you 1 plus 3i, 2 minus I, say, please multiply that out, you multiply it out. No, I'm just showing you how you FOIL it out. You call it FOIL or whatever? Yeah, I'm just showing you how to do that. So here, x1, y1, that will be 1 and 3. x2, y2, that will be 2 and minus 1. And you just follow the same process. Right. Any other questions? Okay. So that will be it for the complex multiplication. The division is a little bit more difficult. We'll do that after the holiday. But just some notation and terminology. So when you're watching your YouTube videos and the guy says, take the real part and the imaginary part, you need to know what that means. Okay, so let's say we have a complex number z is x plus I, y. So I suggest you leave a full page open for this notation and terminology. There will be quite a list coming up. Okay, so whatever page you're on, just leave it open. So you write out these first few things and then leave the rest blank for when we get back. Okay, so the first thing, this x part, we call that the real part of the complex number, and we write it as Re of z. This is the real part. Okay. Then the y, not r times y. Okay, please put a big note there. The y on its own, not with the r. This is equal to Im of z, Im for imaginary part. Okay. So any complex number z can be written as the real part of z plus r times the imaginary part of z. So it will be the real part of z plus I times the imaginary part of z. Okay, again, I think third time now, the I is not included here. Okay, you include the I give you 0 right away. Okay, if it's out of 5, you get 0. If it's out of 10, you get 0. Okay, the y over here for the imaginary part is by itself. There is no I in front of it. Okay. Again, please leave the rest of the page blank. There's going to be a lot more terminology coming up. Yeah. So there will be the conjugates, the arguments, a lot of stuff coming in. Okay. Any questions about this bit? Okay. So in the holiday, when you're doing your reading or you're watching your YouTube videos, if the guy mentions other things, you can stop watching. We're only going to cover that later. Okay. So only up to this part for the quiz. Okay. So a quiz will be from this bit here, the factoring, the polynomials, and this bit over here, complex number arithmetic. Right. Any questions? All good. Okay. So we'll leave it at